So let's see this SDT. This SDT is used to construct a syntax tree or no parse tree. Okay, there is something called as abstract syntax tree and concrete syntax tree. I'll tell you the what it is. See, if I have an expression, let us say 2 plus 3 into 4, and for that if I write like this, e derives, e plus t, t derives, t star f, and then f derives id, t to f, f to id, e to t, t to f, and then f to id. If I write like this, it is called concrete syntax tree, or it is also called as parse tree, right? You know that this is a parse tree, and one more name is concrete syntax tree. So instead of representing these many nodes and then finally representing this small sentence, we could even use less number of nodes and we can represent the same sentence. How we can do it is, we could do like this. So I could write star is having higher precedence, therefore 3 into 4 will be evaluated here, and then plus is having less precedence, which means 2 plus 3 into 4. This is also the representation of a tree, but then this is abstract, which means it doesn't show you the details about the variables. If I represent only the terminals and still construct a parse tree, this is nothing but a parse tree which is called abstract parse tree, and this is concrete parse tree because it is representing everything. Now this SDT is to build this concrete parse tree, this abstract parse tree. Okay, so why do we need this abstract parse tree is, there are various ways in which we could represent intermediate code, and one of the popular intermediate codes is syntax tree. So the output, if I carry out this SDT on any input string, then I am supposed to get ideally the abstract parse tree as output. So let's take the same example and let me explain you this SDT first. You know this grammar. This grammar is expression grammar. E derives e plus t, or t derives t star f for f, and f derives id. It is nothing but this grammar generates all the strings which contains addition, multiplication, and identifiers. Okay. Now let me explain you all the productions and then the semantic action. For this production f derives id, if you look at the semantic action, it is f is having a attribute, and the attribute of f is f dot nptr, node pointer. Nptr is nothing but node pointer. It is it is actually assigning some value from this function. Make node is a function. So make node is a function which will create a node with this with 3 attributes. In this node there are 3 attributes: left pointer, right pointer, and the value. So value is there, left pointer is there, right pointer is there, which means make node is going to create a node with these values and then return a pointer, and that pointer value will be stored in f dot nptr. And coming to this production t derives f, whenever there is this production, whatever is f's nptr, that will be placed in t's nptr. And coming to this production t derives t star f, here I have written t1. It is actually not t1, it is just t. Just to distinguish that right side t from left side t, I have written t1. And here also it is doing the same. We are going to make a node, and for that the left pointer of the node is whatever is the t1 pointer, and the right pointer of the node is whatever is f dot nptr, and the value is star, and it is going to return some value, and that value will be stored in t dot nptr. So I'll take an example and I'll show you how it is working. Let's take the same example, this one only. Let us say we have the example 2 plus 3 into 4, and we should get this as final output, right? So I have constructed the parse tree and I'm actually traversing it using a bottom-up parser. Now there is a reduction. What is the reduction? id is reduced to f, right? So when id is reduced to f, what is the action associated? F dot nptr, which means f will have a value nptr, and into that some value will be written. What will be that value? We are going to create a node and for that the value of the node will be whatever the lexical value of this is. The lexical value of this ID is 2, this ID is 3, this ID is 4, which means we are going to create a node, okay, and now that node will be containing the value 2 and the left pointer will be null and right pointer will be null, which means left pointer is null and right pointer is null, and the starting address of this node will be returned as the value. Now let us say its address is 100. Just for the assumption, its address need not be 100. I am assuming that its address is 100. Then 100 will be returned and that 100 will be saved in f.nptr, which means f.nptr will hold 100. Now f is reduced to t. F is reduced to t. Then what is the action? T.nptr equal to f.nptr, which means whatever was f.n node pointer, that value will come into t node pointer. So what is it? 100. And now t is reduced to e. So whenever t is reduced to e, the corresponding action will take place. What is the action? E.nptr equal to t.nptr. What is e.nptr? Whatever was t.nptr, which is 100. And now this is not a reduction, not a reduction, and again next reduction is here. ID is again reduced to f. When ID is reduced to f, what again this production will take, this production will be used and this action has to be carried out. See this, ID is reduced to f. So when I am reducing ID to f, this particular production will be used and therefore this action will take place. What is the action? We have to create a node, because make node is the function, and its value should be id dot value. What is the id dot value here? Id dot name, it is 3. Name is nothing but, let us assume it is lexical value. Id is the token and name is the lexical value, okay. And now for this we are going to create a node, and let us say the node value is 3 and left side is null and right side is null. Why? Left pointer is null, right pointer is null, and id dot name is 3, okay. And now that, let us say this address of this node is 200, just for the assumption, and now f.nptr equal to 200. Now f is reduced to t. When f is reduced to t, t.nptr should be equal to f.nptr. That is the rule there, which means t.nptr equal to 200. And now this is not a reduction, and again this is a reduction. What is the reduction? ID is reduced to f. Again the same action has to take place, which is nothing but creating a node with 4 as the value, and left pointer is null and right pointer is null. So let us assume that the starting address for this 4, this one, this pointer, this node is 300. That one will be written here, which means this f.nptr will get 300. What is t.nptr? 200. What is f.nptr? 300. Now t star f is reduced to f. T star f is reduced to t. T star f is reduced to t. Then what should be done? Then we should make a pointer, we should make a node. Yes, I am making a node. And what is the value of that node? The value of that node is star. And what is the left pointer of that node? Left pointer of that node is t1.nptr, which is nothing but 200, which means it will be pointing to this, right? And the right pointer is nothing but f.nptr. What is f.nptr? 300, which means this one will be pointing to this. Got it? And next, and now this newly created node, let us assume that its address is 400. Now that 400 will be here, which means t.nptr equal to 400. Now this is reduced, which means e plus t is reduced to e. When e plus t is reduced to e, the production is e plus t is reduced to e, this one. Again we have to make one more node. Yes, I am making one more node. And what is the value of that node? Value of that node is plus, and the left side pointer is e1 dot pointer. What is e1 dot pointer? It is 100, which means this one is pointing to this, and the right side point and the right side node is t.nptr. What is t.nptr? 400, which means it is pointing to this. Therefore, if I carry out that SDT on this input, I am supposed to get this entire thing, right? And if you look at this, this is nothing but the data structure of abstract parse tree for this abstract parse tree. The same thing, right? Just verify this. Plus, plus, and left child is 2, left child is 2, star, star, and star is having left child as 3 and right child as 4. Okay, so this is the SDT which is used to create the abstract syntax tree. So what is the abstract syntax tree? It is nothing but a parse tree in which variables are not shown, and parse tree is also called as concrete parse tree. And one more thing is, in the parse tree, whenever you represent all the variables and when you write the values of those variables, these attributes, any parse tree for which the attributes are written along with the values, that is also called as annotated parse tree. Okay, it is annotated parse tree, and this is abstract syntax tree. It is also called as concrete syntax tree. It is called as abstract syntax tree. Okay, we shall see more examples about this. Let's see this SDT. This is an SDT for type checking. Okay, in order to check the type, we are going to use this SDT. If we have to find out what is the type of an expression, there are three ways. See this, an expression can be either false or true, simply a terminal. If they are just false or true, simply the tokens, then expression type is simply boolean. True or false indicates the type is boolean. If the expression is a number, number means some identifier, right? And then the type of it is integer. If an expression is some other expression closed within a parenthesis, then whatever is the type of this expression inside it, that is going to be the type of the outside expression, which means e dot type equal to e1 dot type. If the expression is e1 is comparison with e2, which means we are checking whether e1 is equal to e2 or not. It is not an assignment, it is comparison, right? If e1 and e2 are compared, first of all, two expressions can be compared only if they are of same type, which means both should be of same type. E1 dot type should be equal to E2 dot type, and either E1, both of them should be either integer or boolean. We can either compare integer values or boolean values. We cannot compare any other values, right? Therefore, both of them should be, coming to this grammar, generally in other grammar we can even compare characters, right? But then coming to this grammar, we have only two types. One is boolean and other is integer. So both should be either boolean or both should be either integer, right? In general programming languages, we might have even other constructs also, but in this grammar we are having only these two constructs. Now first check both of them are equal or not, which means either e1 dot e2 is equal to e1 dot type is equal to e2 dot type. If both the types are equal, then both of them has to be either integer or boolean. Then e dot type equal to boolean, which means if both the types are equal and both the types are either integer or boolean, then the overall expression is going to get a type as boolean, right? Why? It is a comparison. And next one is, when we are adding two expressions, when can we add two expressions according to this grammar is, we cannot add two boolean variables. We can add only two integer numbers, right? So first we should check both are of same type, which means e1 dot type equal to e2 dot type, and then we should be sure that that type is equal to integer. If that is true, which means if the type is integer, then the left side is going to get e dot type as integer, otherwise it is going to be error. So I'll take an example and show you what happens with this. Let us say the example is, I have expression 2 plus 3 into 8 is equal to 8. So I want to find out whether this is meaningful or not, which means is it according to the semantics, is it right? Can I do it? If so, what is the type of this entire expression finally? So always, as I told you, we have to first construct the parse tree, and then you could apply these semantic rules, either using the top down parser or bottom up parser. I am just constructing the parse tree for the example. Parse tree for the example is this. Okay, now it is, we are comparing 2 plus 3 whether it is equal to 8 or not, right? 2 plus 3 are in the parenthesis, and then we are equating it to 8, so that is why equal to 8, right? So now how to find it out is, first you have to traverse the path tree top down, left to right, and then we have to assign the types. Now whenever this E is number, then what is the type we get here? See, I'll be going like this. Yes, E equal to number. This is reduction. What is the production? E dot type equal to integer. Therefore, this E got type as integer. And now again, E number is reduced to E. Then what do we get? E dot type equal to integer. Okay. And now this is a reduction. What is the reduction? Expression plus expression is reduced to E. Expression plus expression is reduced to E. In this case, what we should do is check whether both are of same type. Yes, both are of same type, and both should be of integer. Yes, both are of integer. Then we are going to say E dot type equal to int. See, here this E1 and E2 are not different variables, they are E only. Just to differentiate between the left side E and then right side E, I have given these numbers, right? Therefore, according to this SDT, the type of this expression is going to be whatever the type of the sum is, which means integer. So here the E is integer. And now again one more reduction. What is the action? Reduction is closed brace E, open brace E, closed brace is reduced to E. Then whatever was the type of E1 dot type, that is going to be for E dot type, which means whatever is the type of this inside E is going to be given to this E. Now what is the type of this inside E? Integer. Therefore this E is going to get type as integer, E dot type as integer, right? This is not a reduction, this is a reduction, right? So then what is the production? Number is reduced to E, then E dot type is equal to integer, right? And again this is a reduction. What is the reduction? E comparison E is reduced to E, which means E equal to E is reduced to E. In this case, what we should do is compare whether E1 dot type equal to E2 dot type, which means these two types should be equal. Yes, they are equal, both are int. And then we are going to say the left hand side expression is going to get type as boolean. Okay, so overall the type of this expression is nothing but boolean expression. This is how type checking will work along with SDT. We shall see more examples for SDT. So in this example, I want to do some translations on binary numbers. So you know the binary numbers, it is nothing but all the numbers consisting of zeros and ones, right? So this grammar especially generates binary numbers. So the meaning of this grammar is, a number can be a list of bits, okay? And a list of bits can be a list of bits followed by a bit or simply a bit, and a bit can be 0 or 1. See this, a number can be a list of bits, a list of bits can be list of bits followed by a bit or simply a bit, and a bit can be 0 or 1. Now given this grammar, it is going to generate all the possible binary numbers. Now what I wanted to do is, I want to find out the value of a binary number or do some translations like this. So first of all, I want to write some semantic actions where I want to count the number of ones in this produced by this grammar, or given a string, I want to count the number of ones inside this string using some SDT. So this is the grammar. So I'll write like this: whenever bit is 1, then we have seen 1 1, right? Therefore b dot count equal to 1. I am counting number of ones. Whenever the bit is 0, then b dot count equal to 0, which means I have not seen any ones. And if the production is, whenever there is a list, then the number of bits, number of ones in the list depend on number of ones in this bit. If the bit is 1, then we are going to get list, number of ones in list as 1. Therefore L dot count equal to bit dot count. If the bit is 1, then L dot count equal to 1. If the bit is 0, then the L dot count equal to 0. Now there are two L's. So just to differentiate this left side L from the right side L, I am just writing the right side L as L1. It doesn't mean that L is a different variable. Now L dot count, which means number of ones in this list, is equal to number of ones in L1, which means L1 dot count, plus number of ones in this bit B dot count. Okay, so the total number of ones in the total list is equal to total number of ones in the list followed by total number of ones in the bit. Finally, number of ones in the number dot count is equal to whatever are the number of ones in the C. Now, in the same way, if you want to count let us assume that we want to count number of zeros. We want to count only zeros. Then what should we do? Everything is going to be same. In place of these two, we have to make modifications, right? So whenever we see 0, the count is 1, and whenever we see 1, the count is 0. So if I use these two semantic actions in place of these two semantic actions and leave the rest of the productions or the actions same, then we are going to get we are going to count number of zeros. In case if I want to count number of bits, I want to count all the number of bits. How can I count all the number of bits is just make b dot count equal to 1 and b dot count equal to 1. Either 1 or 0 we are going to count. Then we are going to count everything, all number of bits. It is counting the number of bits. Now, given a binary number, I want to find its value in decimal. So I want to convert a binary number to decimal number using this grammar. Okay, so first of all, I'll just give you some examples here. We have to understand some properties about binary numbers or any number system in general. If I have a number, let us say 1 1. So what is its decimal number? Decimal value is 3. If I have a number 101, what is its decimal value? 5. Now one thing you have to note here is, if I have a number 1011, then how do we get the value of it is, take the first number, first digit, its value is 1, right? Yes, 1. And whenever you append one more digit to this, which means 0, you are multiplying this 1 with 0 and then adding 1 with 2 and then adding 0. That is how you get 2, which means 10 is now 2. Whenever you append one more digit which is 1, one more bit which is 1, we have to multiply whatever was the value of previous number and then add 1. Okay, and so total number is going to be 5. And whenever you append one more digit, one more bit, you have to multiply 5 with 2 and then add that. That is why it is going to be 11. Which means, what I mean to say is, if I have a very big number 10110, something like this, if you have to find out the entire number, you need not actually convert the entire number into decimal. You convert the first part into decimal. Let us say 1011. What is its value? Its value is 11, and multiply with base. What is the base? Base is 2, and then add 0. It is going to be 22. Got it? So in case if it is going to be 10111, then you convert the entire number into decimal value. Let us say the decimal value of this is 11, yes, and multiply with 2 and then add 1. It is going to be 23, right? So using this rule, you can easily convert a binary number, especially for this grammar. For this grammar, if you want to convert a binary number to decimal number, following this method is very easy, because the grammar has been written in such a way that it is inherently providing you help for this kind of translation. See this, how can I do it is, if the bit is 0 or 1, you need not have this count now. So count is not required. You can, without having this count, I just want to convert the binary number into decimal number. See this. So first thing is, if you have this one, then what is it? A bit is either 0 or 1. Then simply that bit's decimal value is either 0, if it is 0, or that bit's decimal value is 1 if it is 1. Okay, and now in this production, what is the value of decimal value of L is whatever is the decimal value of B, which means L dot decimal value is equal to B dot decimal value. And coming to this production, L derives L1 followed by B, L dot decimal value is equal to whatever is L1's decimal value is. We have seen it, right? If I have 10110, then this complete list is L, this is L1 and this is a bit. Therefore, whatever is the decimal value of L1, you take it and multiply with 2 and add the decimal value of B, which means L dot decimal value is equal to whatever was the decimal value of L1. So, L1 dot decimal value into base. What is base? 2 plus B dot decimal value, right? And finally, for this production, N dot decimal value is equal to whatever is L dot decimal value. So using this SDT, we can take a binary string and we can find out the decimal value. I'll just show you with an example. Let us say the string given is 1011 and our question is to find out what is the decimal value of this 1011. Number is going to be a list is going to be list followed by a bit, list is going to be list followed by a bit, list followed by a bit, and a list is bit. So this one is 1 0 1 1. Now we traverse the pass tree like this, and 1 is reduced to bit. Then what is the value associated with this? Bit dot decimal value is equal to 1. And next bit is reduced to L. Then what is the decimal value associated with L? L dot decimal value equal to B dot decimal value, which is nothing but 1. And again there is reduction. 0 is reduced to 1. Then what is it? B dot decimal value equal to 0. And again there is reduction. What is reduction? LB is reduced to L, right? Then what is the value of it? Whatever is L's decimal value, which is 2, 1 multiply with base, which is 2. 1 into 2 plus 0, that is why we get 2, which means till now we have seen 1 0. By this part we have seen 1 0 and its value is written as 2. And again there is a reduction. What is the reduction? 0 is reduced to B. Then what is B dot decimal value? B dot decimal value is 0. Now again this is reduced to L. So list comma bit is reduced to a list. Now we already know that, I think this is 1, this is 1, okay, this is 0 and here this is 1. We already know that this is 1. We already know that the left side list value is 2 and the right side bit value is 1, which means left side bit value list value is 2 and the right side bit value is 1. Now combining these two, we have to take the left side list value and multiply with 2. 2 into 2, which is 4, and then add 1, which is 5. Therefore L dot D value equal to 5. So 101 is nothing but 5. 101 is 5. And again there is a reduction. What is the reduction? 1 is reduced to B. Then what is B dot decimal value? 1, which means left side I have got 5 and the rightmost bit is 1. Therefore what is the value of this list is whatever is left side value multiply with 2 and then add 1. So what is 5 into 2 plus 1? It is 11, which means this entire value is 5 and this entire value is 1. Now adding these two or concatenating these two is going to give me 11. Finally number dot decimal value equal to 11. That is how we got 11. Got it? So this is an SDT where we converted a binary number into a decimal number. Now my question is, what if there is a decimal point for in the binary number, which means if I have something like 11.01, so its value is I think 3.25, right? So what if there is a decimal point inside the binary numbers? If there is a decimal point, then we have to change the grammar and then change the rules in order to find out this value. We shall see that example now.